This is a Module 1 video on alkene addition. I will introduce this in the context of alkene hydrobromination, and will also discuss thermodynamics in terms of the relationship between the equilibrium constant and the change in free energy for an equilibrium reaction. The hydrobromination of isobutene is shown here from the textbook, and to the right, the mechanism is shown from the textbook. I prefer to show mechanisms by showing the equilibrium between each reactant, intermediate or intermediates, and product or products. As a fundamental principle in this class, please remember that all reactions are equilibria reactions. Therefore, all reactions are reversible. In class, we'll discuss this question: how does hydrobromination relate to reactions introduced last semester in Chem 202Z? And this is straightforward, but I will ask you to make a complete and scholarly statement. Turning to page 2 of the worksheet, this briefly reviews thermodynamic principles from last semester. In particular, note that the equilibrium constant is the ratio of the concentration of products versus the concentration of reactants. Furthermore, the Gibbs free energy equation links temperature and the equilibrium constant to determine the change in free energy. This value is temperature dependent. In the second video, I'll describe the difference between enthalpy and entropy and how these each contribute to free energy. Recall that enthalpy is the change in heat produced or consumed, whether a reaction is exothermic when heat is produced or endothermic when heat is consumed. And then the change in entropy for a reaction is energy dispersal, the degrees of freedom and how those change, how the degrees of freedom increase when the change in entropy of reaction is positive. Turning to page 3 of the worksheet, I show some data for the hydrobromination reaction of 2-methylpropene, or isobutene as its common name, to give tertiary butyl bromide. This experimentalist, Howlett, measured the equilibrium constant for this reaction at various temperatures. To fit the data into the free energy equation, temperature was converted into Kelvin. The equilibrium constant was converted into its natural log. And so these are the calculated free energies for this reaction. And note how the free energy increases with increasing temperature, from a fairly large negative number to a number that is approaching 0 at higher temperature. In class discussion, I'll ask you to share your thoughts on how do you think the equilibrium constants were measured in these experiments. If you look at the temperature ranges for these experiments, and the boiling points of both reactants and the product, you'll see that this reaction was conducted in the gas phase. As we scroll down the page, this is an Excel plot graphing the change in free energy versus the change in temperature. There are 6 data points, although 2 of them are taken at temperatures very close together, so they're nearly on top of each other. Finally, I'll point out, be careful not to confuse the equilibrium constant, capital italicized K, with temperature in Kelvin, which is capital non-italicized K. Turning to the 4th page of the worksheet, this is the claim, evidence, reasoning for this experiment. I will ask you to make a claim at what temperature does delta G equal 0. And as part of your claim, describe what happens below that temperature and what happens above that temperature. Then, as the evidence, cite the specific scientific data that supports your claim. And finally, for reasoning, describe the justification that links your claim with the evidence. This concludes the first video for Module 1B.